and welcome back, everyone. This is the third lecture in the series we are having with Xanadu, and Catalina is back with us today. All the lectures with Xanadu are focused on quantum machine learning, and they are very useful if you are targeting the quantum machine learning module we are offering in the WOMANIUM summer program. But these lectures are also important if you are looking to solve the challenges, the industry challenges, which focus on quantum machine learning. So all those participants who want to challenge themselves and try and solve the problems we have posted as part of the Fraunhofer QML for conspicuous detection problem, these lectures are pretty useful. So if those who are just viewing this on YouTube as a recording afterwards, I would recommend going back on the playlist, scrolling above and watching the two lectures from Catalina before, and then coming back to this lecture. But yeah, today, let's get started. Catalina, the stage is all yours.
Perfect. So today, the goal is to have a bit of a conversation and have enough time for questions. And I'm going to poke your brains and ask the uncomfortable questions, right? So we've learned a lot about quantum machine learning. We've learned about what are layers, how do you calculate the depth of a circuit, what are different ansatz, how do you embed data into your quantum circuits. Then we went all the way to talk about variational algorithms, quantum kernels, quantum neural networks, which is kind of a controversial topic. And today we're going to ask ourselves, how do I know if I am, if I am getting a good result with my, my quantum machine learning workflow? So often what you will want, and maybe here I will ask the question, when you do something with quantum machine learning, what are you expecting? What do you want? You probably want to A, solve a problem to a certain level of accuracy, or B, solve it in a certain amount of time, or C, maybe solve it faster than whatever exists right now. So option 1, accuracy, or option A, accuracy, option B, speed, and option C, just comparison to what others have done, just better in whatever metric that is, right? So I'm here in the Discord and in the Zoom, so let me know. And Vardaan, you will tell me if somebody answers in some other avenue. So let me know here in the chat or in Discord, what are you looking for when you do a quantum machine learning project, right? When you're going to do your project, now your final project, or what are you going to measure? How are you going to know if you're doing well or not? So A and B, okay. So speed and accuracy, and somebody else said accuracy. Or if there's another option, write it for sure. If there's something else that you're going to be looking for, make sure to write it. Depends on the task, a trade-off, but speed and accuracy.
Several people are typing on Discord. So to all the participants, this entire session will be an interactive one-to-one session with Catalina. I would recommend everyone to go on the Discord chats, go to the live questions channel, and put all your answers over there.
Mm-hmm. Yes. So I'm saying how to think quantumly instead of classically. Novel approaches. Yes, actually, I think there's one part of it, which is testing things out. There's a novel approach, and we want to see how it behaves. So actually, we should come to the question with an open mind, not saying, I'm going to do this, and it's going to perform better than X. Usually, when you do research, you start with a question. So you're going to ask yourself, how does this compare? And then this lets you actually answer the question much better than if you are specifically targeting one result. Because what will happen is you will be biased. You will be more biased to get the result that you expect. If you ask the question a bit more openly, you of course can have a hypothesis, but I recommend that in general, you approach the problem as a question. How does this compare? And usually if what we're looking for is a speed up, we have to make sure we make a fair comparison. And so what has been happening a lot is that we have not been making fair comparisons. So you're going to be seeing, or maybe you have seen in the past, a lot of papers, research articles, people mentioning, I did a quantum machine learning algorithm and it performed 50% better than a classical one. But what classical one? The best classical one? How do you compare? How long did you spend training and making that super effort to get the classical one to work better compared to the quantum one? And how does that quantum one compare to other quantum ones, right? And so it turns out that for most of the tasks that we have, looked into, let's say there's a data set called MNIST. It's about like handwritten numbers. And a lot of research in quantum machine learning uses this as a base data set just because it's available, easy to use, and to compare. It turns out that we perform worse than all, basically, even simple classical algorithms, right? It doesn't mean that it's not possible, but we have maybe been trying to force answers. It looks a little bit like we're so excited to get it to work that we're not seeing that we're actually not making fair comparisons. And so while some quantum algorithms can perform better than some classical ones, if you actually compare it to the better classical ones, most of the time they perform worse. So this whole session of today is about, asking ourselves, how do you compare better? So Xanadu recently, earlier this year, published a paper. It included Maria Schultz's team, and it's about benchmarking. So I'm gonna share the link. We have a blog. Maybe I'm going to share first the link to the blog so that you can check it later. I'm going to share it on Discord so that everybody who's there can later take a look at that paper, at that blog post. And that's kind of the base of the question for today. What is happening in like at the moment in quantum machine learning is that everybody wants to get their research published. And when you're doing your project or final project, you are going to be confronted with that question of how do we measure? So my recommendation would be to see how other people compare. Remember how when we were talking about what ansatz do I choose? We start with something that we know or something that somebody else has done. My recommendation would be to start with comparing in a fair way. So this is an example of how do you make a fair comparison. If you there are many ways of making a comparison, and it will depend on the specific problem. But in general, if you look at those metrics that usually people say, like speed or accuracy, those are the two that generally, make it to the headline of the paper. For most of the questions, we actually perform worse. And there's a nice graph that I actually want to share. Let me test this. This is one. So you should be seeing this graph from the paper where you're comparing classical with quantum options. So you have classifiers, you have kernels, you have neural networks. And according to different tests, different metrics, they're ranked on whether they were the best or the worst. So blue is best, and orange is worse. And what you see in general is that the classical ones tend to perform the best with the different kinds of tests. So the second one, for instance, remember we saw kernels. You can have a support vector classifier that in general performs way better than quantum quantum kernels or other quantum techniques. And this is even for the ones that we thought were going to perform really well. There are some that sometimes perform better. So for example, Dressed quantum circuit classifier sometimes performs better, which means that it sometimes is blue. But there are some classical techniques that perform better more often. So if you're actually looking at generalizing and looking at different kinds of problems, you will see that in general, classical techniques, convolutional neural nets, for example, compare much better compared to convolutional neural nets. And so this doesn't mean that we should just give up. This is not the answer. The question is, we have to make sure that we are comparing, we're making a fair comparison, and we're exploring different techniques. And when there is one that seems to work, tested, tested like if you were a generative adversarial machine, test when it fails, so that you can actually give the right give the right interpretation for the result, not something that will work for everything, but maybe it will only work in certain situations. And especially for your project, you're going to be looking at one specific data set, and you're going to put all of the tools that you have in hand to look at that data set. And it's important that when you present that research that you have done, the work that you have done, you mention that this is specifically, maybe you found an increase in performance for this one particular data set, right? So that people don't get the impression that it can generalize to other things. So I think this is mention number one. I'm going to look at everything that you're writing on Discord right now. Is there a way that this quantum machine learning pipeline will operate eventually? Oh, okay. I think the question is about what are the domains where you can get advantages. That is the question, and that is what you should try to explore. So today, with the project that you're doing, with the final project of WOMANIUM, you're exploring one area, right? And you're gonna have hundreds of people everywhere looking to see if that one, if you can come up with a solution that works good for that problem. And maybe you'll try that solution for a different problem, and it can work or it cannot. And you have to be completely open to that. So I think that's maybe answers the question. How do you can get better results in a certain domain? You have to test it. There are some people that are doing fundamental research that are looking more into the structure of the problems. In that case, then you can get a general idea for different kind of problems. But I think you have to come with the open mind of knowing that it might not work, and you kind of don't need to kind of force it to work. We're seeing this ourselves. Isn't it, Riza, how complex classical machine learning is? Yes, classical machine learning is very, very complex. And it's something that, you have to acknowledge it works very well. That's great. That's great. And it just, maybe it will give us more motivation to keep working in quantum, to see where they can complement themselves better. Some other option, and this is option D, this is one that is a possibility as well, is doing theoretical work. Theoretical work to show what is called a provable advantage. And so this is what a lot of people, doing PhDs, they're looking for a provable advantage, which is very, very hard and is not always very useful. So let me, this is maybe, I'm going to give an example. It's a little bit out of context, but hopefully I can give you the idea. I did some research many years ago, and I wanted on control systems for a drone. And I wanted to know what was the bound for my control. So if I put this controller on the drone, how far will it deviate from the trajectory that I set? And my bound was huge. It was like a couple of meters. It's a lot. So while I could find a theoretical bound, this bound was not useful for my problem. I wanted something that actually gave me a better sense of like where I could put this drone, right? If your theoretical bound is too large, if it's, you know, tens of meters, well, that's the same as nothing, right? Like I cannot know if I can go put it in a corridor because I'm not going to have a corridor that is that size. So while theoretical bounds can in theory be useful, you have to compare it with whether it's reasonable for your problem. So in my case, I didn't care whether, you know, I knew the drone wasn't going to deviate tens of meters. I wanted something more precise. And this is something that, you know, couldn't be at that time, maybe today, but at that time, it couldn't theoretically prove that it would stay within a smaller bound. So hopefully this gives you, I know that it's a different problem, but hopefully it gives you kind of the sense of these things that we have to look out for. It's not enough just to say there's a provable advantage, but what does it mean in the context of the problem that I'm trying to solve? For example, again, in quantum machine learning, many people talk about exponential speedups. So what does that mean? That as I get more qubits, you know, it will be exponentially faster, so like way faster compared to something else, right? A classical method, for example. But it turns out that there are, you know, coefficients that multiply this that are important. So if I have a straight line and I have a curve like this, you know, it's exponential, maybe they only cross at a point that's already out of what I care about, right? If my problem actually lies within a smaller range, then that exponential speedup, actually, I don't care about that. I probably only want to stay on the first, you know, section of the domain of the problem. So when you're reading and, you know, then doing research, it's not enough to only say there's an exponential speedup or there's a provable advantage. Put it in the context of the problem that you're trying to solve and see whether this makes sense there. So some other problems. This can be, I think, about QML is made superior to the classical analog. Oh, yeah. So very good point. A lot of people put quantum in front of anything classical and it doesn't make it better. It can make it worse. Kind of like using a GPU. It's the same. Not because you're using a GPU will it be better. Sometimes it can be slower. So it's a good thing that you mentioned, Erica. Yes, the question, were all the hyperparameters turned well and blank comparisons are not a great idea? Yes. Great. So I'm gonna continue. How do we benchmark them? Benchmarks, excellent. You want several people trying them out. And so, of course, these are done with rigor and you have like this specific methods. We actually have data sets online so that anybody can try them. And, you know, we have the code and you can replicate it as well. So this is one good option. When you have open code and open data sets and everything, you can have people in, you know, different parts of the world trying it out for themselves and testing whether they get the same result. And they can try different variations of it. So this can spur more, you know, more conversation and more research. And this is kind of a way of comparing those benchmark scenes. And not all, I mean, the benchmarks make sense again in context. So if I'm doing research regarding to like production, like you're going to do for your final project, you're going to try to look for benchmarks that make sense for that. Not if you try MNIST for something that is not about images, then that benchmark doesn't make sense for you, right? Comparing things out of context, again, no, not great. So comparing benchmarks are good, and trying yourself to replicate benchmarks that others have done. That's useful. And there's a comment, we might have ended up using classical machine learning for our quantum machine learning model. This is actually a good point. Why not? Why not? we can absolutely combine them and use classical to improve our quantum stuff. Why not? That is a really good comment. And it may inspire classical machine learning. Actually, we've seen that a lot, also with a lot of the advantage experiments. We've seen a lot that, advantage, supremacy, however you want to call them. When quantum gets to a certain stage, kind of gives new ideas and motivates people to try to beat it. So they both, keep improving. And this is completely valid, useful, great. Somebody mentioning, I remember a while ago reading about whether quantum advantage was an open question, whether we had proof, and whether there might be an undiscovered classical algorithm that could match it. Yes. So there are several things that are important to know when you talk about quantum advantage. One is there are different meanings for different people. You have to make sure that you are meaning the same thing when you're talking to something else. In the experiments that showed what we call quantum computational advantage, which has also been called supremacy, what they care about is something that computationally can prove or shows better results than the classical algorithms at that time with the best classical systems at that time. So, for example, when the classical machine learning beat somebody at chess many years ago, I don't know what years was that, like maybe in the 60s, there was this classical machine learning algorithm that beat somebody at chess. So they beat the best known, adversary at that time, right? In the same way today, when people talk about quantum computational advantage or supremacy, they usually mean how do you compare with the best known classical alternative at that time? It doesn't mean that in the future it cannot change, it might, but that's computational advantage. Now there's the other question about, let's say, more practical advantage, and that one is still like open for you to discover, to explore, to be part of it. What is super exciting about being today in the field is that you can be part of that. There are so many open questions, and you can help find the answers to that. So I recommend maybe joining, if you want, a research group or a collaboration. You don't have to do everything on your own. Being part of WOMANIUM hopefully will help you collaborate with everybody who's here on the Discord, so that you can get a little bit of that, other ideas that will challenge yours. So somebody talking about MP problems. Yes, so these are more about computational complexity. It's a valid approach, but usually when you're targeted with a real world application, and that's what I think everybody is trying to think about right now. What are those real world applications? Usually, the person in production is not going to tell you this problem is NP hard. They're usually going to say, I have the specific problem. So while it's valid to go from a theory perspective and look at NP hard problems, etc., if you're looking for practical advantage, that may not be enough. Okay. So somebody explaining NP hard, that's great. There's a mathematical proof that Grover's algorithm and Shor's are superior to current classical analogs. Okay, good question. Shor's algorithm is a great example because, yes, I think it's probably one of the few examples where you have shown, or it is shown, that it is, it has been proven that it's superior to classical analogs. So that's amazing, and hopefully we'll be able to use it for something useful. For now, It's just making us rethink the way we encrypt information, because our encryption is based on RSA, which would be in the future vulnerable to that if we have large enough quantum computers. Grover's is a little bit different because it depends on when you start looking at the problem. So if you look at how do you embed the data in that quantum computer, then it becomes less evident that there is an advantage, right? So the mathematical proof starts with some assumptions, starts with assumptions that you can create an oracle efficiently, starts with an assumption that you can encode information efficiently, which is not always the case. So that is important also to have that critical thinking of, they've told me this is, mathematically proven, but what exactly is it? What do they assume? What are the assumptions? Always make sure that you look at the assumptions and you state any assumptions. Because for many algorithms, including Grover's, some of the assumptions are on the fact that you can create an oracle, and it's not necessarily the case. So that is a really interesting point there. Okay, oh, good point as well. We don't have the hardware to scale yet. That's true. And a lot of people are now moving away from NISQ, so noisy intermediate scale quantum. The field in general is moving, and people who are doing research and are at the front of what's going on, they're looking into more like intermediate scale quantum, no longer caring about the noise. We're assuming we're going to be able to fix that, but looking at the next kind of problem, the problem where we can imagine we already have error correction, and we're looking at small fault tolerant or early fault tolerant computers. And the question is what we can do then. A big part of what is going on right now is how many gates, how many qubits will I need to run a specific algorithm to solve my problem well? And that can help redesign. If you know how many qubits, let's say maybe you have quantum phase estimation is a very, very important one, but it requires so many qubits. So how do you tweak it to require less qubits? And how do you estimate how many qubits will you need and how many gates will you need to solve a specific problem with a variation of these algorithms? So that is something that is an open question at the moment. So good points there, everyone. Pessimism is essential. I don't know if I would phrase it as pessimism. I think critical optimism, I'm gonna coin this term. Being optimistic because, you shouldn't stop when things get hard. And actually, some researchers say the best researchers know when something is too hard that actually you should change direction, or when something is just hard but not impossible, and you should actually keep going at it. And it's something that I think you will learn with experience, so hopefully you'll be able to get some of that experience with the projects that you're doing. You have to be optimistic but critical as well, so that you know when to keep going even if it's hard, and when to change direction. Great. So a lot of comments about Shor's and Grover's. Oh, sorry, I messed up the date. I see somebody corrected me about the chess. It was 1997. Sorry, I thought it was earlier. So, question, has quantum machine learning already surpassed classical machine learning at all? So here we come to the base of the question. Some people will tell you yes, because there are specific situations when you have shown advantages. So in the graph or the table or the diagram that I showed you before, in some cases, quantum machine learning algorithms do perform better. So there are situations where quantum machine learning has surpassed classical, but not in all situations, not in all cases. So That's why this benchmarking experiment was very interesting, because it's easy to stay with saying, for this situation, it worked better. So in general, it works better. And that's not what we want, right? So I think that's a key message here. If it worked better in one situation, doesn't mean that it will work better in any situation, or that it's better in general. So in some cases, yes, quantum machine learning, there have been examples where quantum machine learning has surpassed classical, but we cannot say it in such a general sense, or like it might give whoever is reading that message the wrong idea in that sense, right? How are we sure that we are making a fair comparison? Let's start with you doing your best, all right? And you have to go with the right mindset of, if you are trying to compare quantum and classical, you should compare the best with the best, not the simple with the best, or the one you spent 30 hours training on with the one you spent 5 minutes training on. So let's start with that, and also see how others have compared. And I'm sure people will come up with metrics that can help you compare better. But starting with that is a good option. Asking yourself, even just asking yourself the question, am I sure that I'm making a fair comparison? That's already the first step, and it will probably lead you in a good direction. Okay, so somebody says, this program is about quantum machine learning and quantum AI, but it seems like nothing practical in the near future. Oof. So again, we come to the question about pessimism and optimism, right? I want to be optimistic about it. And like, there's so many people in the world, very smart, doing research on this. And there have been situations where they have shown an advantage in specific cases, right? So it's not that there's no advantage at all. There have been advantages in specific situations. So the question is more, is there something in general that works better? We don't know. Is there some general algorithm or technique or some general advantage? That is an open question. For specific problems and specific situations and assumptions, etc., there have been advantages, or there is hope in that sense. But whether there is a general advantage, that's still an open question. That is, in research at the moment, that's a problem you could try to answer as well. Somebody says, for my project, I wanted to use QML, but the system does not get trained well because the hardware's being not developed yet. That's a good point. So a lot of the research today happens in simulators because the quantum hardware is expensive, hard to access, has a lot of constraints. So you can start doing research using simulators that will give you a sense and help you compare. However, something very, very important is, if there is an advantage in a simulator, it doesn't mean, you should always test it in a quantum computer to say that there is an advantage, because there are things that happen in the quantum computers that don't happen, in simulators. So you can say there's an algorithm, a quantum algorithm that shows an advantage in a certain situation, but for it to be considered actual quantum advantage, it has to run on an actual quantum computer. So that's an important point as well. You can do a lot of research, and you can, let's say, show that certain algorithms compare better with respect to classical ones. But quantum advantage itself requires a quantum computer, which is hard today. Yes, the computers are still being developed, still being obvious. All right, so somebody's saying, we were able till now to get very high accuracy for 6 classes with around only 180 images per class out of the 6 classes, and you have to work on your data, answers, and cross function. Yes, absolutely. Working with your data is key. If your data is not well set, then you will probably not get the answer that you expect. So a lot of the work actually happens, in looking at the data and working with it. Yes, somebody's saying quantum machine learning is not a broad spectrum antibiotic, neither is classical. You have to diagnose according to the problem. Yes, absolutely. All right. We have a lot of questions. I think we'll have time to get to them all. Yes, but keep asking the questions. Does classical computing have the same problem of calculating the amount of gates and qubits when it is implemented? I find a bit demotivating that one needs to calculate those for each quantum algorithm because we still don't have an actual quantum computer. Oh, the reason why you want to calculate those gates and qubits is because you want to know whether your algorithm will be implementable in a near future. That's the reason why you want to care, why you care about the gates and the qubits. It's because we know that in an intermediate future, you will have quantum computers that will have maybe a couple hundred qubits, and you will be able to run maybe several thousand gates, maybe 10 to the something, but you won't be able to run an infinite number of gates with an infinite number of qubits. So this is why you care. It's more about thinking of that intermediate scale, or like medium-term application, something that you could run in a quantum computer that has limitations in the number of qubits and the number of gates that you can run. So that's the reason why you care. If you don't care at all about that, let's say, for example, for Shor's algorithm, you need way more than that. And it's a super important, result, very, very important. It motivates us to keep going and try to find something like that. But it requires so many more qubits and so many more gates. It's something that will happen in the far future. It's something that will probably be implementable in the far future, but not yet. So if we want something that is implementable sooner, that's when you care about the gates and the qubits. But you can do, you can absolutely do research on problems like Shor's. This is very, very valid, very useful. So I don't want to discourage you from doing that kind of research. It's also super valid. What are limiting instances whereby you get a classical machine learning algorithm directly from a quantum machine learning one? I don't understand the question, so if you can ask it again, I will make sure to answer that. What algorithms have been more successful so far? Oh, actually, then let me go back to what we had before here. So here, these are some examples, and there are many others. When it's blue, it's so in the x-axis you have number of rankings. So let's say it's like the number of tests. And when it's blue, it means that it has performed the best out of the group. And when it's orange, it means that it has performed the worst out of the group. And not all of the tests can be done with all of the algorithms. So that's something important to take into account. So in the case of quantum ones, for example, DRESS quantum circuit classifier, it performed the best in several situations, except that the classical one performed better in more times, more often, right? So this DRESS quantum circuit classifier seems pretty good. It performed the best in many situations, but it didn't perform as well as some classical ones, like data re-uploading classifier. So hopefully this can give you the sense of, yes, sometimes they perform better, or which ones perform better. DRESS quantum circuit seems to be performing well for classification. A projected quantum kernel seems to be performing moderately well in many cases. Convolutional neural network, not applicable to a lot of situations, but in some of them, yes, it does perform better. So all of these have situations where they perform better, but if you just compare them overall with all of the other, let's say, all of the other options that are out there, they're not the one that performs better most often, right? So hopefully this can clarify that. That's all right. So somebody answers, in classical computation, there are already highly optimized adder and subtractor multiplexed circuits, which are used as building blocks to solve more complex problems. Yes, there are some problems that are already optimized in classical. And again, this depends on what your goal is. If your goal is to add 1 + 1, you don't need a quantum computer for that, right? You already have enough speed and accuracy and everything you need with a classical computer. So that's why we care a lot about these very hard problems. And sometimes it's about the speed or the accuracy, something that will be maybe prohibitively expensive to do. So let me give you an example. For some situations, you will need like a wind tunnel, for example, right? If you want to do computational fluid dynamics, it's very, very expensive to do with a classical computer, and there are techniques and they work well. But for example, if you want to design a Formula 1 car, I don't know if here somebody likes Formula 1, but when they design it, they have to put the car inside of a huge tunnel that has like air coming into it, and then they can measure how the air moves around the car. So that's a wind tunnel. And their time in those tunnels is very, very limited. Those systems don't exist everywhere. They're, expensive, hard to use, etc. And so you cannot use it for everything. If they had infinite time to work in a wind tunnel, they will probably do that. But they have limitations on how much they can do it. So instead, they have to go to very computationally expensive classical techniques, classical simulation that take a lot of time. So this is something that is prohibitively expensive to do in other industries. Formula 1, maybe they have the money to use that wind tunnel, but for some other industries, maybe they cannot. Or maybe they don't kind of do it as often as they would like. So some questions are even more about like, maybe it's very expensive. Maybe it's a money question, right? So part of that, let's say, part of that practical advantage, I think, should also include, is it economically feasible to do it, right? If it will cost you more to do a simulation than to do the actual experiment in the wind tunnel, then you will probably use the wind tunnel. But if you can instead use a simulation, whether it's classical or quantum, that can, give you good results to the certain accuracy that you expect, and with the time frame that you expect, and that is actually cheaper than using that wind tunnel, then maybe you've got a solution, right? So hopefully this again like forces to ask the question, because sometimes there are situations where it looks like the quantum computer, maybe it looks more accurate, maybe it looks faster, so great, we've got everything. But it turns out that it's so much more expensive. So we will actually prefer to spend a little more time, marginally more time, to run it in a classical computer instead of a quantum one. So if your question is about, for example, I don't know, I'm going to say, how do you package a box better? Maybe if you're Amazon, right? How do you package the boxes better? How much money are they willing to invest in that? Maybe you will find a marginal increase if you use a quantum computer, but will it actually make sense for the business to adopt that solution? That's a different question. That's a little bit of the practical question that is involved. And I think it's a further challenge. It's not something that you have to, be super aware of in general. Like, it's still valuable to do research on this, even if it's, not economically feasible today. But it's something to have in mind, something to take into account. Sometimes those problems, maybe they'll take longer. And I've heard of situations like these where sometimes a problem takes longer, but it gives you more accuracy, or it is less expensive, or something like this. So this is something also that you can consider as part of the whole question. Okay, next question. How about some terms such as QGAN? Can using entanglement surpass classical GAN? such as mode collapse or so on. So using entanglement is critical. If you don't use entanglement, it's unlikely that you will find an advantage, but it's not enough. So it's not enough to say, because I added an entanglement, then it will be better. That's not the case. So kind of that's the question. Just adding entanglement or anything quantum is not enough to make it, surpass anything classical. Classical models work very well for many situations, including GANs. So having a QGAN will not necessarily work better. It might, but it not necessarily. Would it be possible to use the formalism of QDITs to gain more advantageous use cases? Excellent question again. So QDITs are when you don't only have like 2 states, but you could have like 3 or 4 or more. So 3 are called Qutrits and more QDITs. We actually have simulators in Pennylean for Qutrits. So you can test them out if you want. So what happens is, from an information point of view, it's in general better to use 2-level systems than 3. And this is the same as what happened in classical. So in the classical world, when we didn't yet have, everything established, some people were thinking about having 3-level systems, because in the end, it's just a voltage, and you decide, depending on the level of the voltage, whether you classify it as a 1 or as a 0, and depending on that, you make the computation. And some people thought, well, how about having 3 levels? But it turns out that it's much harder to distinguish between those 3, and there's more likelihood of having errors, and everything becomes more complex when you have 3 levels. And you can do the experiment. You have a ruler, and you have to, and the question is it on the right-hand side or the left-hand side? The question is much easier than if you're asked what third of the ruler do you have your, dot on. So 2-level systems are in general chosen from an information and practicality point of view. There's so much more that you can do with 2-level systems. Maybe, and there again, analog systems still exist in the classical world. It's possible that they will still exist in the quantum world, and maybe QDITs will be useful. But for now, and this is the reason why everybody talks about qubits more, is because from an information point of view, it makes more sense, practically speaking. Okay, in the beginning of classical computation, I know that we used to have room computers, but I want to know if there was some trouble. Oh, I think this was commenting about a previous question. So today in quantum, we have these room computers, and you've seen it probably in the lab tours. You've seen that quantum computers take, they're not something small that you can put in your pocket. They take up a lot of space. So yes, today we have maybe not room-sized, but very big quantum computers. So any advances in quantum computing similar to natural language processing or large language models? Some companies have been looking at that, and there are techniques to do that. I think classical large language models works just so well that it's hard to know, but it's an open question. I mean, it's fairly recent that all of this has started. So I would, yeah, I don't know. I guess the answer is, I don't know. I know there are companies that do that, but how advanced they are, I'm not sure. Okay, so I think we're almost out of questions. Oh, somebody asked, the benchmarks that I was showing for QML, they have been run on classical computers, yes. Okay, I think we're almost out of time and questions. So if you want to write your last question. Some people say these quantum machine learnings feel like classical algorithms. I don't know. I think they're referring to a specific paper. I don't know what paper that is. So somebody else talking about how classical was in the past. Okay, I think it's a little bit too long. Let me look at this last question. I think we should divide quantum machine learning into two categories. One, explicit quantum hardware enable, and the second one that could be run on classical computers as well. Yes, that's possible. I think part of the goal and why everybody's excited about quantum computers is that at some point your classical computers will have limits. So, for example, in Penny Lane, we're doing our best to build the best simulators possible. We're always improving them, you know, making them able to simulate more and more qubits so that you can run things there, even very large. But at some point, there's a limit. And this happens to me very often. I see people's questions and they show me this huge molecule. And it's like, I'm trying to run this huge molecule, but my program fails. And the answer is, unfortunately, yes. If it's something that is too large, your computer will not even have enough memory to store, you know, the state vector, to store the state of that qubit. So at some point, you will be limited and you will need a quantum computer, but you can start doing a lot of the work. And I think you're doing it now, just being at WOMANIUM here today, you know, having this conversation is part of the process. And for now, I think you can start working with simulators. And if quantum computers are available and very large and great in the future, then you can use them as well. Maybe just time for one last question, 1 minute. What is the key difference between Penny Lane and strawberry fields in terms of quantum chemistry function? Why calculating ground state on Penny, but vibrating spectra on strawberry and Gaussian boson sampling? Good question. And I think great to finish today. Gaussian boson sampling is a problem that at Xanadu we have quantum computers. We have quantum computers that could solve that very well. And Borealis, which made the headlines everywhere, was an example of that. So it beats the best classical algorithm at the time with the best classical hardware at the time. However, Gaussian boson sampling, we couldn't find any practical use for it. So that's super sad. We had this amazing quantum computer that would solve problems better than classical, but we couldn't find any practical application. For vibronic spectra, for example, it turned out, and we did that research internally as well. So we hired chemists to help us see how vibronic spectra would compare with the beautiful, great quantum computers that we had compared to the classical ones. And it turns out that the classical ones won. So we had the question, we tested it ourselves, you know, we put in our like a hat of, we're gonna make classical work better, and we succeeded. So in the end, we couldn't find any practical use for Gaussian boson sampling. So, you know, it's still an open question. Maybe you'll find one and then we'll just rebuild that computer and everything will be great. But for now, we didn't find it. So my recommendation would be always to use Penny Lane instead of strawberry fields. Strawberry fields is more about photonics and like very, very specific, very niche. So I would recommend in general to use Penny Lane instead. I mean, if you do happen to know about an advantage with Gaussian boson sampling, then that's great. Make sure to publish it. But for now, we couldn't find any practical real world advantage there. So I think we're done with time. Vardaan, let me know. Yeah.
Yeah, wonderful. Thanks a lot, Catalina. I think you mentioned some really interesting points, and this I feel a good moment for all the participants to reflect upon what type of solutions they want to build for the project, and also start thinking about some of the critical ideas you presented today, right? Like, should we aim for speed or accuracy, or should we rather take a step back and actually start comparing the solution we're building and rather have a hypothesis going on instead of just aiming for one single solution? So I think these are really good points. And yeah, to all the participants, Catalina is also available on Discord. So if you do have any specific questions, or just ping her over there, I'm sure she would be happy to answer them. If you do have more technical questions about Xanadu, about using Penny Lane in general, I would recommend you hop onto the Slack channel for Penny Lane. The whole community is over there, so you can answer all your technical questions over there. And yeah, even if you are facing certain problems with the project, something is not working, maybe you are having difficulties installing the Penny library, for instance, yeah, just either put it on the WOMANIUM Discord. We'll relay the questions to Catalina and her team at Xanadu, or you can directly ask the team on the Penny Slack channel.
Yes, and actually, I'm gonna put it in Discord. The place for questions, where I'm there answering questions always, is our discussion forum. So discuss.pennylane.ai. So that's the place where you can go and ask any questions that you have. So thank you for the invitation, Vardaan, Marlu. Oh, and everybody, remember, if you complete the Quantum Machine Learning Challenge, you'll get a certificate. So I guess Marlu and Vardaan can tell you more about that.
All right. Yeah, thanks a lot, Catalina, once again.